Hi, my name is Dr. Matthew Michal. I'm a lecturer of mathematics at NJIT, and through this video series I'm talking about differential equations, and I'm working my way through the arc on the Boyce and DePrima textbook examples and theory, so that you can learn about how to think about the textbook. As you read something, what are the things I want you to really see and highlight? So this, even though it's a section 2, I typically like to do this one first because it goes really well with chapter 1. Because in these techniques, it's just building upon the techniques we've used in the previous chapter. This is just sort of like an applied Calculus 1 or Calculus 2 section. The subject boils down to the idea that for some equations, for some differential equations, it is possible to separate the variables to a dy or a dx. So all the y's on one side of the equal sign and all the x's on another side. Another thing to note that they must be multiplied by their proper differential. So the y's are multiplied by dy, the x function is multiplied dx. So this could be dx divided by x terms or dy divided by y terms. But nowhere should the dy be multiplied by an x, or the dx by a y, or dt by anything other than t, or some constant. If I'm able to divide the equation by the equal sign and have one of each variable on either side, this equation is known as a separable equation. Here's an example. If I move the y's to the left and the dx to the right, we get only y's on the left and only x's on the right. This is just a simple integration. Choose which side you want the c, the constant, because these are indefinite integrals, and we get an implicit solution for our problem. And notice it would be very difficult to solve explicitly y equals and then a function of x. It's possible, but it's probably not worth it. Notice we have corners or cusps right here and right here at what looks to be y plus or minus 2. And so it's okay, especially with separable equations, to write solutions implicitly because it really works well for it. Here's another example. Notice the x terms are all on the top, the y terms are on the denominator, so it's easy to separate them. This is not to say that I can't separate dy dx is equal to x times y. That's also very doable, as long as you can multiply or divide the x and y terms apart from each other. We are fair game. So notice this is once again a nice easy problem to just integrate and solve implicitly. But because the y term is quadratic this time, whereas last time it was cubic, it is possible to use the quadratic formula in terms of y in order to get an explicit form. Whether it's worth it, I don't know. I like having it implicitly. It works nicer because take a look at that plot of the graph using a direction field. We definitely are failing the vertical line test. And so the explicit expression for y is only going to be able to contain the top half or the bottom half, not both. And that's why we're going to have to choose a specific plus or minus. Notice I have to choose the minus because of my initial condition. This is saying that at x is equal to 0, y is equal to negative 1. So that means I'm interested in this black arc here. Notice if I was to plug this into the implicit expression, I would be able to include both the top and bottom arcs, both the black and green arcs. But because I'm choosing to do explicit in this case, I have to choose a color. Do I want black or do I want green? Do I want plus? Do I want minus? And that's why I like using implicit. I get all of the terms. One thing that is good about it, though, that I will say, that sometimes it really explains why we're not going to be able to plug in any x values to the left of -2. So it's really showing the domain. And the domain extends all the way to y is equal to 1, right? Because notice the denominator. And this extension can go as far over as y. We have a problem with vertical tangent lines at y is equal to 1. And that at x is equal to -2, right here, I'm always going to get a y value of +1, because notice this term is equal to 0. I can't move it any farther over. And that means for this, it's as far as it's going to go. So it does explain really well how we're going to deal with the domain of this graph. But it's not necessary per se, but it is useful. Here's another example that we can work through. Notice, move the y's to the left, dx is up and to the right. Solve for c. And we're going to get y's and x's on the left and a constant on the right. Notice, though, we are changing the constant. Here we have a constant in terms of a lowercase c, whereas here we have the constant in terms of an uppercase c. Note that uppercase c is 4 times this lower c. And it makes sense because nobody likes having fractions in your graph. We'd much rather have this as your function. It plays nicer. You can understand it better. So by multiplying the left and right hand side by 4, it's more workable. This is not to say but here's the thing, we don't particularly care because both of these are constants. We only particularly care what this constant is once we plug in the initial condition. So if I plug the initial condition in here, yeah, I'm going to care that this c value is going to be 17/4. And then I'm going to have to track its changes throughout the whole thing. But if I wait to plug in this initial condition, so everything is all set and set up, that's going to be a lot easier. And then I just need to track changes in c. So since this is the first constant, sometimes I'll notate this c1, then c2, c3, c4. Sometimes I've gotten as far as c10 or c12 and all the different manipulations I'm going to do. And I'm just noting that this is a different constant than there was before. It doesn't particularly matter as long as you're keeping track that there are changes occurring. And notice in this case we have interesting what might be called orbits, right? So we're having these two peaks here and it's kind of branching out from here, or this could be two valleys, right? This could be like we're in the middle of a valley, and so we have different pits forming here. And so in this case, implicit is really the way to go, because quartic y means even though I might be able to find an explicit y value, it's really not going to be worth it. And you can really see the usage of this with the red graph being the one we were considering before. Lastly, you can kind of consider these as parametric equations as well. It's not necessary, but it is helpful to understand that, hey, I have this initial condition at 0, 2. Well, look at the arrows. The arrows are saying I'm going to travel along this arc. So if I have t values here, I consider that at time t, this is what's going on. And so these parametric equations are seeming to apply the x and y values, your position and position and y, is determined by what time period are we talking about. Not necessary, but it can be helpful understanding and working with these equations.